So in the previous video, we looked a whole bunch at Planck's hypothesis, okay? And of course, Planck's hypothesis had a lot to do with basically light acts like little tiny bundles of energy, which was a very big different type idea compared to what most people are used to considering light to be at the time. Now, we're just going to do some basic practice with it a little bit, show you a couple of little things, and then we're actually going to connect it to something that was introduced to you guys in grade 11, and then we can expand on it a little bit, and then of course it's going to lead into other things as well. So let's just start with some simple little practice here of how this type of thing actually works. So let's just take something really simple. Suppose we got a 6.2 times 10 to the 15 hertz light wave or a photon coming in, or a bundle of energy, whatever you want to call it, and we want to know how much energy it has. Okay, well, we just got to use Planck's hypothesis, Planck's equation, and that's pretty straightforward. Energy is basically just HF. So we got the Planck constant, the 6.626 times 10 to the negative 34. We multiply that by the frequency. We just got to take those two numbers and multiply them. And if we multiply those two, it's going to be a really, really small number, but we multiply the two together, and looks like we get around 4.11 times 10 to the negative 18 joules of energy, or like that's the energy of the energy bundle for that frequency and wavelength of light. Now, it's a really, really, really small amount of energy, so it's really common to convert this type of thing into electron volts. I showed you guys electron volts in your other stuff that you guys have done. So if we divide that by that, the 1.6 negative 19 conversion factor, we're looking around 25.7 electron volts of energy. Okay, so it's actually a pretty simple calculation. Planck's hypothesis has major implications, but the actual basic calculation is pretty simple. So let's take something similar. Suppose we've got a little 1.2 electron volt light bundle coming in. We want to know what the wavelength is. Well, first thing I'm going to do, I'm going to convert this into joules. So I just got to multiply that by the 1.6 negative 19 conversion factor. And we're looking at 1.92 times 10 to the negative 19 joules. And then I can calculate the wavelength. So of course, energy is equal to HF, but it's really common, frequency is equal to speed divided by wavelength. So you'll often see it written as hc over lambda. It's a really common variation of the expression. And we can just rearrange, and wavelength, of course, would be hc divided by E. Well, we know the H value, we know the speed of light. We divide by the energy, we did the conversion already. We just got to punch things out, and it looks like we got about 1.04 times 10 to the negative, not 16, negative 6 meters, which would be 1.04 micrometers, and that would be the wavelength of that light. Okay, so it's a pretty simple calculation. It's not too bad. And of course, what we're going to do is I'm going to show you what this connects to. We're going to connect this actually to something you were first introduced to in grade 11. And then we are going to build on it. We'll expand on it a little bit more because you got a little more background knowledge now. And then we will also then connect it to other really similar types of phenomena and applications and properties and stuff like that. Okay, but first I'm going to show you a little something else. It's actually a sheet. It's a similar version of a sheet that you guys actually had in grade 11, and then we're going to go through that and highlight a couple things. All right, so hopefully this sheet looks a little bit familiar. It's a little bit different than the one you had in grade 11, but the basic idea is the same. And it's about Einstein and the photoelectric effect, which he won his Nobel Prize for. Now, of course, the particle theory, that Newton developed the particle theory, did lots of great stuff with that. We looked at the wave theory as well, shown by the Huygens principle and the Young experiment to be true. And we've also looked at Maxwell's equations and how he sort of theorized that light could be a combination of electric and magnetic fields, don't need a medium to travel, which made the electromagnetic wave idea. And these are all things that we've looked at before. And what we're going to do is we're going to sort of take Planck's hypothesis and then sort of continue the story of this. And again, hopefully this sounds a little bit familiar from grade 11. So what Einstein wanted to do is he wanted to study why metal exposed to ultraviolet light would emit electrons. So basically there's photons or packets of energy coming in, hitting metals, and electrons are jumping off. Now, this was observed by two other people, I think one in the 1840s and 50s, and one in the 1890s, I think it was, about 50 years later. One, I think, was working with a conductive solution. I think one was looking at just some metal antennas or something like that. And they noticed that when it was exposed to ultraviolet light, they would get sparking or increased conductivity. Now, they didn't research it. They didn't focus it, I guess, too much. It wasn't the focus of their work. But Einstein came along and wanted to try and explain why it worked. Now, if you go with the wave theory of light, says the energy should build up until the electrons have enough energy and they will then jump off. Now, you typically don't see this because most light that we are familiar with, the energy is really low. So if that's true, you just have to wait longer or make the light brighter. And if you make the light brighter or wait longer, more energy will be absorbed, and eventually the electrons will jump off. And of course, both of these ideas failed miserably. Neither of these things worked. The wave theory of light had no explanation for what was actually going on. So luckily, Planck's hypothesis was, close around the same time, and Einstein then, hey, let's try applying this new idea and see if it works out. So Einstein said the electrons were being knocked off by a bundle of energy called a photon, and this was a perfect application of Planck's hypothesis, this particle idea. And of course, it worked really, really, really well. Basically, if the light was too low, below what's called threshold frequency, the packet of energy, the photon, doesn't have enough energy. It's too weak. It's like a little bullet. The bullet's too weak in order to knock off an electron. It doesn't matter how long you wait. It doesn't matter how bright you make the light. It makes no difference. That little photon is too weak, not enough energy to shoot off an electron. It doesn't matter how long you wait. Doesn't matter how bright, doesn't make any difference. Now, if you get past that threshold frequency, you will start getting electrons moving because you've got enough energy. So if you go past that threshold frequency, the electrons start coming off. And if you keep on going past the threshold frequency, the electrons actually come off faster and faster and faster. And if you use brighter light or more intense light, you actually get more electrons coming off. And there's no waiting. This happens right after it actually hits the material. Okay, so this was the basic idea. And again, we went over this a little bit in grade 11, so hopefully this is sounding familiar to you. But now we can, of course, expand on it a little bit more. So if we look at the basic idea of generally what's going on, the basic idea is pretty simple. First things first, the photon energy comes into the situation. Okay, that's pretty simple. Then, of course, once it comes in, you have to give some energy to the material. Let me move that up a little bit. There we go. So the energy's got to be paid off with, the material's got to be paid off some of that energy, and that's called the work function. And that's what this is right here. That's the work function right there. Sometimes you'll also see a capital W. I like to use the Greek letter phi, partially because it just looks fancier. But I typically use phi. You'll see W, capital W sometimes. But so there's that threshold frequency right there. So you got the HF, which is Planck's hypothesis. The energy comes in. The first thing that energy has to do is pay off the work function. You got to pay off the material. And if you don't have a high enough frequency, you don't have enough energy, you can't even pay off the material with the work function, nothing's going to happen. But once you get past that threshold frequency, once that frequency gets higher than that, you have enough to pay off that work function, plus you can then have some left over. And that leftover energy can then be the kinetic energy of the electron. And I found this great graphic, this nice little graph right here. I can't remember where somebody gave it to me. I can't remember where it came from, but it's a beautiful little diagram graph here of the situation where over here, you're starting down here on your frequency axis going sideways. This is low frequency, this is low energy, low frequency, nothing happens, nothing happens, nothing happens until you get right there, until you get to that threshold frequency. Once you get that threshold frequency, all of that energy that you had prior gets absorbed as the work function. And then anything past that, this is where the electrons start firing off, and this is where you start getting your kinetic energy. And of course, as the frequency keeps on getting higher, the kinetic energy keeps on getting higher because the electrons still keep coming off, and they keep on going faster and faster and faster. Okay, so that's the basic idea behind the photoelectric effect. It's all conservation of energy. Energy's coming in, pay off the material, and then anything left over goes to the electron. Okay, so let me show you something else that shows this really nicely. All right, so here's a great little simulation that's going to show what we're talking about really, really nicely. We've got a little light source going on. I'll even turn the light here a little bit. There you go. There you go. Got a little bit of orangey type light coming in there. And it's hitting a piece of metal. It's set to platinum right now. And the light's hitting there and nothing's happening. Now, according to the wave theory, we've got energy coming into the metal. And the material is absorbing that energy. And if we wait long enough, eventually electrons should start jumping off. Well, it doesn't matter how long we wait, it's not going to happen. The same way, if I make this light brighter, we shouldn't have to wait. Well, it doesn't make any difference, because it doesn't matter how bright we make the light, it doesn't matter how long we wait, nothing's going to happen. So we sort of now apply Planck's hypothesis and Einstein's idea. Basically, according to Planck's hypothesis and Einstein, the light's coming in, but it's just too weak. The energy is too weak. It doesn't have enough punch in order to release the electrons. So to increase that energy, we need to make the frequency higher. And we can make the frequency higher by reducing the wavelength. I'll tone the intensity down just a little tiny bit over there. Yeah, nice little school bell in the background. Okay, so we've got the little intensity. We'll tone that down a little bit. And now what we're going to do is we're going to take a little slider here, and we're going to start moving it down in order to increase the frequency by decreasing the wavelength. Now you can see, hopefully you can see over here, there's a little tiny graph as well. There's a little electron volt energy frequency graph. And you can see there's a little slider at the bottom there that's going back and forth as I move this slider back and forth. So as I am decreasing the wavelength, the frequency is actually getting higher, and still nothing's happening. And we're going to creep into the ultraviolet. You can see that it's creeping to where that little purple line kicks in, because that is where we should start getting, and there we go, we start getting electrons. Okay, so we need to get to that threshold frequency, and if we sort of creep this thing back and we look at the graph, let's see if we can get it nicely right about there, close to there. Right where that little nub thing is, right where the graph is actually starting. That would be the threshold frequency. Oh, got one coming off. So really, we got to go a little bit back a little bit. Okay, so right there, right where that boundary is, right there. It's really close, right in the axis there. We're pretty much at threshold frequency. So right now, there's energy being absorbed by the material, and it's pretty much perfectly matching the work function. So there's nothing really left over for the electrons. But if we go past that, now we can start getting electrons. All right, and if we go even further, we decrease the wavelength and increase the frequency and increase the energy even more, the electrons will start coming off even faster, because now they got even more kinetic energy. All right, so we can actually pull this back a little bit. See, got nothing over there. We're too low. We got too low of a frequency, and then we can go higher, something like that, and then we get the electrons coming off. Okay. And that's the basic idea. Now we can actually change the material as well. For example, here, let's if we take take sodium. Okay, sodium is way over here. Okay, sodium has got a way lower work function than platinum does apparently. So over here, if we've got this purplish color for sodium, you got electrons coming off. You go to platinum, you got nothing, because platinum's work function is higher. You require more energy in order to get it to actually work. We can try copper. Copper doesn't work either. Zinc doesn't work either. Unless you can find where zinc is going to kick in. Oh, there's zinc over there. Okay, and that's the basic idea behind it. Okay, again, go too low and you get absolutely nothing. As you watch the electrons creep across. Okay, so that's the basic idea. Light shines on there, and if you have that threshold frequency and you go past that threshold frequency, there's no waiting, there's nothing. Those electrons started jumping off right away. Okay, so let's get rid of this. We'll go back to me drawing a little bit here. We'll get rid of this. There we go. And let's sort of like summarize a little bit about what we're sort of talking about here. Okay, so let me change my color here. All right, so we are looking at the photoelectric effect. And let's sort of see if we can summarize and diagram some stuff out here. And the actual idea is pretty simple. Here's one of my favorite. I like to draw things out. Okay, so we got like a piece of metal, whatever it happens to be. And inside this metal has a work function. Okay, so, and again, I like to use phi to symbolize my work function. And the way I like to think about it is it's sort of it's a payoff, is what it's how much you have to pay off the material with. Okay, so let's just make up some values here and stuff like that, and let's sort of see how this works. So suppose I've got a photon coming in, and let's say it's low energy. Okay, you've got a low energy photon coming in, right? Maybe it's 2 electron volts, but my material has a payoff of 5 electron volts. Well, if only 2 electron volts is coming in and the payoff is 5, nothing is going to happen. You're going to get absolutely nothing going on. Now, what if we crank it up a little bit? Let's crank it up a little bit, and suppose we have like a medium energy. So maybe a medium energy photon comes in, something like this, right? Maybe it's 6 electron volts. Well, this is more than the work function, so we can actually get something to actually happen here. And if we do that, we should get an electron to come off. And that electron is going to come off. There's my little electron. It jumps off. And that electron would have 1 electron volt of kinetic energy. Because the photon came in with 6, it gave 5 to the material, and there was 1 left over for the electron. Now, if we crank this up even more, okay, maybe we got like almost missed. What if we got like a high energy one? So we got some high energy. Maybe it's, let's go here, 8 electron volts. All right, so it comes with 8 electron volts. Well, again, we've paid off the material. An electron's going to come off, and it's actually going to come off even faster than the first one. And that little guy right there, well, we had 8 electron volts coming in. We paid the material off with 5. That little electron is going to have 3 electron volts of kinetic energy. So again, it's going to come off, and this guy is going to come off faster because there's more energy left over for the electron to actually use to fly away or to move. Okay, and that's the basic idea. So if we sort of like summarize this a little bit and piece things together, it's all about the conservation of energy, which of course is one of the most important conservation things ever. Like, I mean, that's super, super important. So basically you've got energy in, okay, so you've got energy coming into the situation, and of course this is from the photon. And this is where Planck's hypothesis, that's, the whole HF thing from Planck's hypothesis. Now that energy goes to 2 places. So that energy that comes in, it goes to 2 places. Here it goes to, first of all, it has to go to it's got to go to the work function. That's the first thing it has to go to, is the work function. That's the payoff that we talked about. And then second, and that's the second part is sort of like an option, because if there's anything left over, and it has to have leftovers, basically the leftovers go to the electron's kinetic energy. Okay, so you got the energy coming in. First it goes to the work function. Hopefully you can cover that payoff. And if anything got left over, it goes to kinetic energy. So if we sort of put this all together, we've got the energy coming in, we've got the photon energy coming in. It then splits, and this is the same expression that was sort of on the sheet that we went through a little while ago. The photon energy comes in. The first place it goes to is the work function, and then anything left over will be the kinetic energy of the electron. Okay, but you got to get to that threshold frequency. If you don't have that threshold frequency, you don't have any kinetic energy, right? So that's sort of like the key right there of how to find out whether or not you're going to get electrons. You got to know the threshold frequency, find out that minimum energy, and piece it together. Of course, a really common thing for them to do is to actually adjust frequencies to find out when the electrons actually do come out. because if they're right at that boundary, it's really like in the simulation I showed you, when you're right at that boundary between electrons coming off and not coming off, you know you must be at that threshold frequency. And sometimes you'll see an expression, sometimes you'll see, it's on that sheet that I showed you, threshold frequency, the work function, because sometimes you'll see that as well. Because if your threshold frequency, there's no extra energy left over, and the kinetic energy basically becomes zero and is just sort of off of the expression, okay? And this is the basic idea behind the photoelectric effect. And of course, this is the basis for simple solar powered, like solar powered calculators and solar powered chargers and all. That's how there's little solar panels, like little toys with little solar panels to make them move and stuff like that. That's how that works. The light comes in, it hits the specialized material that has a relatively low work function, and it gets the electrons to jump off, which then creates electricity and powers those little things. So you guys have actually been using, especially like solar powered calculators have been around for a long time. I'm sure you guys have had one or used them. That's a perfect little simple application of this, as well as there's lots of other things as well, but that's a really, really common everyday one that you can see for this no problem. So in the next video, we'll do some number stuff and do a couple calculations. The calculations are actually really straightforward. They're not, it's all about finding energies, adding them, subtracting them, and finding different things. It's actually pretty straightforward. It's relatively easy. Okay, so we'll start looking at that in the next video.